Sophie Dabo from the University of Lille. She will talk to us about investigating spatial scan statistics for multivariate functional data.
So first of all, thank you so much, Valeria, Letterio, and all the team for inviting me. It's a great pleasure. It's my first time in Torino, and I hope that it's not the last. Okay, so like Valeria said, I'm originally from Senegal. I'm working in France, in Lille, in the north of France. I don't know if you know where is Lille. It's very close to Paris, Belgium, etc. So today I would like to talk about some topics where I'm involved during the last 20 years, namely it's spatial data and functional data. I try to explain what is functional and spatial data for perhaps colleagues who are not familiar with. And this is a joint work with two of my PhD students, Mohamed Salem Ahmed, who is from Mauritania, Camille Frémont, France, and one colleague from the Hospital of Lille. So in this talk, two terms are important, spatial and functional. So we are dealing with data that are localized in space, and space may be something very simple like latitude, longitude, or something more complex, time and space data. And another point of the kind of data I'm dealing with is that they are functions in time, or it may be shape, images, or more complex dynamical object. So, and usually when dealing with spatial data set, we have dependency between the data set. And in statistics, basically, independent and identity distributed data are the most usual context, but when you have time dependent or spatial dependent, you have to model the correlation or the dependency between the data to be able to have a very relevant estimation or inference procedure. And I would like to cite this famous sentence of Toblock, say that everything is related to X, but new things are more related to the distant sense. And so the specificity of the method I would like to talk about here is that taking into account the fact that the data, they have spatial components that may be some spatial dependency to model, and the fact that they are not usual data set like real value or multivariate, they are functions of time, of space, etc. Okay, good. Thank you. Okay, I'll try to summarize the kind of data and model I will talk about here and show you. I will not give some very theoretical results, just give you the ideas side and show you some numerical application of the clustering method we are dealing with. So here the topic of scan statistics, spatial scan statistics, is to detect clusters in a spatial point of view where a random variable or a set of random variables we are interested in are observed in a, let's say, the places like here in the north of France. This is the region where I live in Lille, we call Nord-Pas-de-Calais. If we look at, for instance, pollution data, PM10, and then we see that in this part, there is something very high, the level of incident. So the level of pollution is very high or very, very low, okay? So in cluster detection or spatial scan statistics, we would like to detect clusters where the variable we observe is anomaly high or anomaly low. And if this data occurs, like here we look at the time dynamic of pollution concentration during a month or a year. This is the x-axis you have. And then all the data are time, usually in time series, you take the data at like, if you have 10 points, you take the data valued in R10, t equal to 10. But if you have a number of points, let's say 100 or 1 million time point, taking a variable valued in R100 or 1000 is very complicated. And if you have a replication of this kind of curve and you take two pollutants, so an alternative to multivariate time series model is what we call functional data analysis. Thinking about these data are functions living in a functional space, a rich space, where the information is more exhaustive than discretizing the point. And functional data analysis date began, I think, at the beginning of 20th, and there are some famous guy working in Italy, working in functional data analysis in Spain, France, and now all over the world. So this is the kind of data. Another example is, for instance, if you would like to identify block spots or black spots, sorry, based in environment or health, etc. Like here in the incidence of COVID-19, where here you only have a, let's say, cartography of the incidence in France, decomposed in region or department here. So what is going on here? It is really, what we observe is really high or not. So to be able to detect statistically in a significant way, instead of doing only unsupervised clustering, like using K-means clustering, etc., if you test in addition that this is a cluster with a certain level of confidence, then this is what we call scan statistics, spatial scan statistics. So, like I said, two words are important: spatial data and the data are in terms of functions. Okay. So just to summarize a little bit, so spatial data or spatial statistics is this part of statistics where data are collected in space, okay? And usually the basic case is that the space is like fluid and longitude, like if you look at the temperature or air quality or some concentration index in a given location, and the location may be the house, a specific position, or it may be a department, a region, etc. And then spatial statistics is all these technical statistics that deal with spatial data. And usually, like I said, spatial data are dependent, and this is a hot point, how to model the spatial dependency and include it in supervised or unsupervised statistical method. And just to summarize a little bit, spatial statistics were applied by Daniel Kreiser, engineer in South Africa at the end of the teens, and it was, so he proposed prediction methods based on spatial data, and this prediction method was formalized mathematically by George Matron, and now spatial statistics is using in statistics, in data mining, data science, etc. Okay. So the other point of view of the kind of data we are dealing, okay, it is the functional. So spatial functional data, spatial data and functional data is what I'm here. So let's say that S is the set where I observe some variable. So S may be here the map of the non-particular region, or it may be France, etc. And for this region, at a given location may be a postal code, postal dome here, and we observe two kind of pollution data. We look at the average PM10 and M, etc. So here are the curves observed at each location. So each curve is related to each location. So if we model it in a probabilistic point of view, I would say that the data set here comes from a collection or a family of random variables that are the next set is S. So S is a point here, and ZS in an observation is an observation. Okay. So this is what I call random fit, and the functional point of view is that this curve comes from a given, let's say, people space of function, for instance. So in summarize, so since the data are functions, okay, so we need to define the proximity, for instance, or a norm or metric in this functional space. So the classical real valued data, in this case, we all know that the Euclidean norm or inner product is very convenient if we generalize to dimension D, meaning that I'm taking the average of temperature or the average of air pollution for a given pollutant, I would say T is equal to 2, and then we can use the Euclidean linear product. So now if the data I'm dealing with are functions, like the function I showed you, let's suppose that these functions are square integrable. So in other words, they are the square of the function, the space of square integrable function. And in this case, a natural way to extend this inner product, and this is well known in the functional data analysis literature, is using this integral. Okay, integral of x of t, y of t, where x is a concentration at a given location, and y also is let's say the temperature at a given location, and the t is the time dimension. So t may be more complex. So summarize the random variable or random fields I'm dealing, since they are paired, will be called functional data. And when we call random functional variable is a variable taking values in a functional space, okay? Meaning that x is as x of t, where t is 1 dimension or 2 dimension or 3 dimension, whatever you want. If t is 1 dimension, it's like time series, it's a curve. If it is 2 dimension, you have an image, maybe MRI image, for instance, or the map, the temperature map in a given region at a fixed time is a data. And if p is larger than 2, then you have complex structure that may be modeled using functional data analysis. Okay, so going back to the problem we are interested here, detecting clusters in some regions by using tests, not only using unsupervised clustering, but detecting and testing if these values are significantly higher than the other place of the region, given a certain confidence, okay? Let's say 95% of confidence, or the level of the test equal to 5%. This is an example of COVID-19, for instance, in France. So to deal with, they use spatial stand statistic. What is spatial stand statistic? It is a statistical test able to detect, so aiming to detect clusters in a spatial point of view. And usually in the literature, we have 3 types of tests to detect clusters in a spatial region. You have tests of spatial aggregation tendency. Going to detail, we have tests based on a priori knowledge, okay, where you use it in the test, this a priori knowledge, meaning that we know that there is a black spot somewhere, and then we use the information here to detect other clusters around. And the other alternative here, called spatial statistic, is detect a cluster using a regression model and without a priori knowledge, okay? Without any, let's say, blind, we detect clusters, and then this detection is combined to a regression model and a test. In other words, we are interested to test null hypothesis. There is no cluster, okay? The distribution of the variables in the whole region is not so different. Even if you have some variation, you cannot say that this place in the north of France, the pollution is higher than the others. The difference is not so significant statistically. Compared to H1, there is at least one cluster, and a cluster may be composed of several postal codes or departments, like what I showed you. This this cluster has to be found, or these clusters have to be found. So this is the test we are dealing with, and then these tests are related to a model we put on X, in other words, a regression model, and then we estimate this parameter related to the cluster detection. Okay. Just to show you how it works, let's take the region. This is my region, and my region is composed of sub-region or spatial unit. You have the spatial unit, and this is your region, and then you have a number of finite spatial unit, and the number of points you see here is called N. Okay, N is a number, or the sample size. Here is illustrated, but the sample size may be very high. So scan statistics is very famous since the previous seminal work of Pidov and his daughter. So first of all, we have to scan all the region. Okay, we have to find all the spatial location or subdivision so that the variable we are interested has higher value or lower value, abnormal values, okay, or extreme if you want. And extreme is something Professor Ali know very well because he specialized on that. And then one hypothesis, our main hypothesis is that we suppose that we are not interested to detect more than half of the sample size. Okay? Any sample size, we would like to detect all the subdivision where there is something higher or higher than the other place or lower than side. So capital W is what we call potential clusters. And then we are looking at in these potential clusters, the location where the value is higher as a statistical test. So let's say that at the first place, I detect this, okay? The scan process detects this, and then I'm scanning all the region to see. The second step, then I detect another cluster, etc., since I scan all the region, and then I look at all the potential clusters, okay? And after that, all the potential clusters, then we underline the most extreme cluster, etc., We call the principal cluster and then the secondary clusters. Okay, so we're going to scan all the region and look at all the potential clusters, and then we do the test and decide regarding the power and the level of the test which subdivision are really clusters. Okay, so first step, we scan all the region. And second step, we look at a concentration or concentration index or statistical test, if you want, that I call CW, potential clusters. And then we look at in all the potential clusters, capital W, the cluster that maximize the concentration index. Concentration index means that somehow a statistical test that is able to detect the cluster. Okay, and what I call MSC would be now the Argmax of the maximum of this cluster within this concentration. And there are different types of tests used. Very, let's say, simple tests will be using ANOVA function, okay, comparing the mean of the functions in a potential cluster to the other locations, etc. And so since this clustering or test, a spatial test is based on somehow a model, then we have to estimate the parameter of the model, okay, the inference parameter of the model. And here we did it. And so in addition to Monte Carlo study, to be able to calculate the power of the test, the level of the test, etc. So before we begin this work using multivariate functional data to detect clusters, like we would like to combine several PoliTo to detect the part in North-Pas-de-Calais or the North region in France or in France, where the pollution is higher, not only based on one pollutant, but several pollutants. So in the literature, there was several parametric and non-parametric methods available for univariate finite dimension or multivariate data. And at that time, there was only one method able to count, to model univariate functional data, meaning that only one pollutant is studied. So since in a high number of applications now we have available more and more available data in time, in space, multivariate makes sense, taking several pollutant or several variables and studying together these variables. We found that it was relevant to find to produce such methodology for the multivariate scan statistic detection, and then we extend first of all the approach that was available in the literature using only one univariate, and then we propose also other methods, and then we compare all these methods with the existing method in the literature. Okay, let me just so the sampling setting is like this. We have n location. the region as we are interested is like here. The N location I denoted S1 to Sn, so N location at the subdivision. I don't know if you see the subdivision here, meaning the postal code at each location. And for each subdivision Si, we have a curve. This is the data set supposed to come from a collection of random field valued in a functional space, like the square integrable variables. And in practice, we have, even if I use functional data analysis, but in practice, we have raw data. You have data like this, okay? So how to convert this data to functions, okay? For that, we use basis expansion, okay? We can, convenient, since I'm working in the space of square integrable variables, I can use any basis function, orthogonal basis, for instance, in this. Then it may be based on spline or principal component analysis or etc. or other basis functions. So here, basically, we use B-spline, principal component analysis also to, and non-parametric also smoothing to transform the raw data to functions. And these now are the observation of the functional number variable we are dealing with. This is the first step of functional data analysis, transforming the raw data to functions before using the methodology. Okay, so after having function, now you have x, y, x, and r functions. Are these smooth curves transformed from the raw data? And then we're going to test there is no cluster, okay, and there is at least one cluster. And the cluster will be detected in the whole shape of the function, not only the peak, the maximum, or the minimum. Okay. So like I said, I'm going to quickly summarize the three kinds of tests we use here. You all know what is Wilkinson Whitney. So here we use, we first of all extend what exists in the literature in the multivariate case, in the one-dimensional functional case, to the multivariate functional one. So ANOVA function, ANOVA model was used, MANOVA, let's say, MANOVA was used here, Wilkinson Whitney or Hotelling test also in the case of function. Let's look at the MANOVA, the functional MANOVA case. Okay, in the functional MANOVA case, like in ANOVA model, we're going to test here mu is the functional mean. Okay, in a potential cluster W, we're going to test H0. The mean is constant in the whole region. Okay, versus there is at least one location where the mean is different to the other. So mu WC is the other. Okay, one cluster compared to the others. And then to summarize this bit, so we're going to compare the mean, the global mean, X bar is the global mean of all the samples, with the mean in the cluster, okay? So with the mean of the cluster, and then we're gonna use this concentration measure based on comparison between the global mean, the mean in the cluster, okay? And yeah, this is between the cluster and between and the cluster. So this LW will be considered as concentration measure. And then we're going to look at the potential cluster where this concentration is higher, maximum. This will be called this kind of BCS based on functional MANOVA. The M is for multivariate. Okay. And then another one, the second one is a Hotelling test. It's based on the extension of the Hotelling test to the functional multivariate one. Exactly. So using like for comparison between the mean in the cluster and the mean outside the cluster. And this sigma is the estimation of the covariance matrix. Let's say covariance operator if you want, because since data are functional here, this is the covariance operator, and this is not very complicated to understand. And then based on this concentration, also this Hotelling test, we underline a concentration measure, and then we outline the cluster where the concentration measure is higher. And the last test is based on the Wilkinson-Whitney. So this is the Wilkinson-Whitney based on multivariate rank. And without entering into detail, we propose three main tests and just three main tests. one based on functional ANOVA, let's say on ANOVA, the other one on Ottling test, and the last one based on Wilkinson-Mandel branch. And from the inference part, like I said, we use Monte Carlo after estimating the parameter U based in the spatial dimension, in the spatial interaction between the location. So with Monte Carlo point of view with M. So we use scan statistic on the permutation here, calculating the power of the test and the type of error. If you fix 5%, say in the Monte Carlo simulation, then we are able to estimate the type error for the one. Let me show you how it works shortly in simulation, and yeah, it's a bit late. Let's say here we simulate by putting, first of all, we choose some hotspot, some cluster. Here we say that the cluster is here and would like to detect it. So we simulate using functions, using here the Fourier basis function, for instance, and we simulate several functions to here, and then these functions are correlated, and the correlation is based on this variable that may be Gaussian, exponential, etc. So in other words, let me take three kinds of clusters. So the cluster is that in this location I showed you the red point. So the curves are higher. We have high values compared to the rest of the world. So here you see it in shape region. The other one is that it's similar to the first one. So the cluster is detected like here in all the time dimension. Then you have the red curves here. I don't know if you see, this is the cluster we would like to outline. And then the Monte Carlo based on one simulation and most 1,000 permutation with a fixed type of error, type 1 of error 5%. And this is a little bit different. The last one is different because the fact that these locations are clustered means that they have a peak. The maximum, they have a maximum value. We see that compared to the first two examples, this is very different. Okay? And the smoothing is a hot point here. Do not miss the peak. Okay, so based on this, the result is that the correlation we have between the multivariate function increase, then the performance of the test decrease, and then the two models based on Wilkinson-Mandel and Ottling was more performance than the MANOVA one, and this is not surprising. It is only the case in the multivariate scan statistics. And just to finish with an application to the real data, where here we collaborate with colleagues from the Hospital of Lille, Vermont, where we have the previous data, and then we look at several concentration here, pollution concentration, NO2, O3, and the 2 PM here you have during 1 month in 2021. And in fact, we do it before, during the pandemic situation and after, and clearly differences. So these are for two pollutants, what we have to show you. So this is the raw data, the basic raw data. So after smoothing, this is what we have, okay? So we outline, if you use the multivariate scan statistic without using the functional, meaning that the point are discretized, okay? Like we use time series model. So the method are only, the non-parametric method available in the literature is only available to detect location in the north of France, in North Pas-de-Calais, very close to Belgium, Pas-de-Calais, where the pollution here you see is detecting only places where the pollution is not high. But if you would like to detect for two pollutants, the place where the pollution is higher than elsewhere, like Lille, it's the center, then using the functional point of view is better. You see that here we detect Lille and then at the part where the pollution is higher. So this conclude show that using the functional point of view, permit to lose information. We are trying to take all the information available in the whole function, including the peak, the minimum, the variation, the shape of the function compared to multivariate one. And among the three methods we propose, two of them are gave better performance than the ANOVA one. And one hypothesis, I did not insist a lot in this, but that the cluster, you see that the circular cluster we are detecting, the clusters we are detecting are based on circular cluster. This is also something that may be relaxed by using rectangular cluster, etc. And this is well documented in the literature. One thing we are working on also is taking curves where the time point is different, because you can record at the station, you can record at a some given time point. At another station, the time point may be different. And in this case, you have unequal or irregular functional data that may. And if you are interested to see, we developed our package here named HD Spatial Scan that is available on the ground with the paper available already published in our journal, where you can apply, have some example here. The pollution data are available on the website, and apply it to other cases if you want. Okay, thank you so much. And
thanks a lot, Sophie, for this very interesting presentation. Is there any question or comments from people who are sitting in the room? Or maybe from people that are online, if you have any comments or questions?
Yeah. Thank you, Sophie, for your presentation. Now I have one question about, I think, the slide 50.
yes, in the smoothing, right?
Okay, yes. My question is about the transformation of points to curves.
Yes.
How to choose the coefficient A and the function phi? Is using the wavelet theory or not?
Oh, yes. Wavelet function may be used also, but in fact, it depends on the kind of data you are. If you have data that are periodic, for instance, Fourier is better. And then we know that Fourier is better even if B-spline may also be used. So B-spline is the most useful function in the literature, but it depends. It should depend on the characteristic of the function you are dealing with. But B-spline or principal components or Fourier basis function or wavelet may also be used.
Okay. Okay. Thank you.
Or non-parametric smoothing also, using kernel smoothing may also be used.
Okay.
Thank you, Sophie. I just want to comment that it would be nice to test your system in Torino, because we have a very good ground for testing polluted air, and please help us to understand what to do. Okay.
I have a question for Sophie, Valeria.
Yes. Yes, please.
Okay, thanks, Sophie, for your nice presentation. I have a question about the application of these methods to count data. For example, in epidemiology, we can be interested to a number of deaths or number of infected persons. When the data are not in R or in when the data are count data.
When data are count data, exactly.
Yes.
Yes.
Can you apply this method to this?
Not yet. We will be doing, because after this paper, we extend it to survival data set.
Okay.
And then now the survival will be included to in the package. And the next step would be to apply it in count data using, because you see that in survival, it may be seen as count data. In fact, if you see recurrent data set, yeah, this is the next step. Kenny and I will work on it.
Okay, thank you.
Thank you, Aliu. Thank you, Sophie. If there is any other comment or question, then if not, let's thank again Sophie